All right, so today I'm gonna be explaining this important paper. Like the past two videos, I was talking about constraint generation, constraint graph generation. But this paper is a particular type of modality. Is used for path. I mean the path that the car is going. So the car in that path, the cars first of all they should be on the ground. You cannot put any place. Also, they shouldn't cross each other. So these are the constraints that they are using. So they introduce this manually bridge diffusion. In fact, they define a distance that when distance is 0, it means that the constraint is satisfied. So this paper recently in AAAI 2025 is important, but I will show in the last slide that why it has several limitations. But it's a very interesting idea. So we describe a novel framework for diffusion-based generative modeling on constrained spaces. So we introduce manual bridges, a framework that expands the kinds of constraints that can be practically used to form so-called diffusion bridges. I have a playlist for Schrödinger bridges. These ideas are related, can be related, but the Schrödinger bridge is more general. And it's, if this is flow matching, and if this is diffusion, this is a stochastic interpolant such as this Schrödinger bridge. You can define your own stochastic interpolant. So we develop a mechanism for combining multiple such constraints so that the resulting multiply constrained model remains a manual bridge that respects all constraints. We also develop a mechanism for training a diffusion model that respects such multiple constraints while also adapting it to match a data distribution. So you see here, MBM applied to traffic scene generation. The goal is to place vehicles on a given bird's eye view image of a map. So indicated here as a light region of the underlying aerial image, the model output is set of cars. So the output is set of cars. Infraction-free cars are green. Cars involved in infractions are yellow. And the top row shows samples from different models given the same map. So the basic background of this is the forward diffusion. You represent it by a stochastic differential equation. Then once you have learned this score, then you can do the reverse step to get the score, and you can minimize with simple approach. We call this a score matching. I have a playlist for score matching. So this paper, Vincent, I think is the second video of that playlist. And so here, constraint generative modeling, they define this diffusion bridge. Of course, it has been defined by these two references, but it's a kind of Brownian bridge process, and requires constraint boundaries to be explicitly stated. So we have a constraint set omega, which is a subset in RD, a function. So when we say b omega of xt and t, a function defined on set. So this function is defined on set, is an omega bridge for the reverse process if the solution at the final time are guaranteed to be inside this space. At the boundary is guaranteed. Like in financial mathematics, at the boundary you like to have some value that you are interested in. So the initial condition and the particular time that you are focused on is important. For example, a particular time such as t. You want to know the x of t. So we draw from pi distribution, and this v you write it like this because you can represent it like that. Now here the extra injected term, as you see this extra injected term, the extra injected term that, this one is extra injected term. So the reverse process, you can write this, but this is the extra one. Because we have already included the score inside the V. So the G2 of B is what we have defined, which will vanish. So extra injected term is quantified through external constraint function, which drifts the particle to move towards the boundary and stay inside. So we need to understand these two definitions. What is omega distance function? Let L be a continuous and almost everywhere differentiable function with finite gradients with respect to x. We call L omega an omega distance function, because when you say any element at any time from 0 to t, then it gives you a distance. A distance should be positive. That's why this is important. And we call L distance function when it is 0 on the region omega that we are interested in. So on this region, your distance should be 0. The second definition is the manually bridged model. So we add this extra B term. As I said here, we have an extra term. So our score, we can put it inside the score. Of course, it doesn't have meaning, but you put it inside the score. Intuitively, the added manual bridge term just guides the distribution towards omega, nothing more. Manually bridged models correspond to score functions of distributions of these four. So they proved two propositions, proposition 1 and 2, the second one combining manual bridges. They want to say that the space of manual bridges is closed. And here you can see the score function or architectural variants. The latter three, these are latter three. These three use the same manual bridge, with the last notably, this one, including an additional path for bridge function. For bridge function gradient not previously considered in the literature. Each diagram shows a single denoising step. In these diagrams, the input T to the model is omitted for conciseness. So generalizing proposition 1, one can combine multiple bridges. So what is the connection between their concept that I defined with the diffusion bridge that we know? Our manually bridge models give rise to reverse STEs similar to the diffusion bridge. So to see this, we can plug the manually bridge score function, and you can see that V now, V is the same, but this is equivalent to 6 once B is defined. So in order to guarantee that solution of STE, it lies in this region omega, when the solution, when you solve it, the bridge function must satisfy this requirement, such as this expected Polyak-Lojasiewicz condition. And this greatly restricts the set of allowed omega distance functions. So it restricts generality of combination of bridges And this thing is very good for continuous domain. You can do Lipschitz constraint, any kind of constraint on that. But when you have combinatorial thing like graphs and language, it's not just about how you control the derivative, how to restrict it, how to confine it. It's not about that. It's more about how do you deal with these combinatorics in graphs. So this paper has some limitations. So this is the visualization of checkerboard. Also, their experiments are very limited to this kind of cars and this example, checkerboard constraint example. So for manual bridges, we use this minimization as a distance function. And sigma is the total amount of noise added at time t of the diffusion process. So their experiments, they compared the standard diffusion to the manual bridge. And for traffic scene, we need measures like collision, off-road, infraction, or elbow. These three are very important for cars, for traffic scene generation. And so this is not mentioned in this paper, but I have written here the limitation. So first, it requires differentiable distance function, but discrete combinatorial ones like graphs is not defined. You should define it by yourself. So that may be a challenge. The second one is model complexity. Adding bridge terms can complicate the training and it's able to be more delicate. It more be very difficult to train this kind of thing. It's very unstable. The focus is on continuous space and diffusion. If your domain is discrete, as I say, like graphs and molecules with discrete constraints, you may need adaptation. And also the empirical evaluation is promising, but perhaps limited in scale. One needs to test how well this scales to very high dimensional, like full scene generation of vehicles and environments. Although combining constraints is addressed, the interactions or couplings of constraints could still be tricky when constraints conflict or are mutually exclusive.